Okay, I want to look at section 2.9 on inverse functions. And first of all, the function needs to be one-to-one. Now we know for the definition of a function that every x must be used and have a unique or exactly one y value assigned to it. Now for the inverse to exist, every y must have a unique x. So every x has a unique y and every y has a unique x. Now for a graph or a relation to be a function, it has to pass the vertical line test. Vertical line passing through the graph exactly once. For the inverse to exist, it passes the vertical line test to be a function, but now it passes the horizontal line test for the inverse to exist. That is, every horizontal line will intersect the graph no more than once. So I want to look at, first of all, I'm going to look at a linear function, f of x equals 2x plus 5. And I'm going to be graphing it, but I want to be able to write the equation of the inverse and the steps that I need to follow. 1, I'm going to change f of x to y. That's step 1. Step 2, switch x and y. 3, solve for y. And 4, write your answer in inverse notation, which is, it as a superscript -1, it means the inverse of f of x equals, and then what you get for the equation. So these are the 4 steps. So step 1, f of x becomes y is equal to 2x plus 5, and then switch x and y. So x is equal to 2y plus 5. Step 3, solve for y. So I'm going to subtract 5, and I'm going to divide by 2. And step 4 is to write your final answer in inverse notation. So the inverse of f of x is equal to x minus 5 over 2. Or you could split it up and write this as 1/2 x minus 5/2. It's the same thing. So either way, depends on what I want to do with it. If I want to graph it, then I probably wanted to put it in the slope-intercept form. But if I'm not going to graph it, I certainly could leave it in the inverse, with the inverse notation, and then just leave it as x minus 5 over 2. Equals 2x plus 5. The inverse of f of x is equal to x minus 5 over 2. Now, algebraically, this is the format I'm going to use, rather than the slope-intercept form. I will use that in a few minutes. So now what I want to do is the composition. I want to do f of the inverse of f of x, which is the same as f, and then in parentheses, the inverse of f of x. Now, we just talked about composition, and the inverse goes into the function. So the function had 2 and then an x plus 5. And in place of that parenthesis, I'm going to put the inverse. And simplify. Can divide out like factors. And then I have x minus 5 plus 5 is x. So when I put the inverse into f of x, I get x. That means this is the identity function. If I put in x, I get out x. Let's check the inverse of f of x. And now the function f goes into the inverse. The inverse had x minus 5 over 2. In that parenthesis, I'm going to put the f function, which is 2x plus 5. In the numerator, the plus 5 and the minus 5 cancel out. And then I have 2x over 2, which is x. So what happens is, if I put the composition of the inverse into the function, or the function into the inverse, I get the identity function. And this is significant. First of all, I'm going to graph the function f of x. This is already in the slope-intercept form. And that is, I'm going to go up 5 for the y-intercept, and then the slope being 2, I'm going to make it in a fraction. The denominator, I'm going to go to the right 1. The numerator, I'm going to go up 2. So I'm going to go over 1, and I'm going to go up 2. Now I can continue to do this and get more points. You could have used a table of values. You could use the x-intercept, y-intercept method. There are a number of different ways that you could graph this. But this is the graph of f of x. Notice it passes the vertical line test to be a function, and it passes the horizontal line test to be 1 to 1. Now let's take the inverse and graph that on the same axis. Now I do want to write this as 1/2 x minus 5/2. I want to put it in the slope-intercept form. Negative 2.5 is the y-intercept, and the slope being 1/2 means I go to the right 2 and I go up 1. Now, what I notice here is that the function and its inverse are symmetric. And they're symmetric over the line y equals x. Because the function and its inverse, as a composition, remember we got x. We got the identity function y equals x. So algebraically, I showed it to you with composition, and graphically, I showed it to you by showing that they're symmetric over the line y equals x. This is true with every function and its inverse. I just happened to pick a linear function because it was easier for you to see.